Algebra 1, here's your practice problems for lesson 4. So first thing we're looking at here is to describe how the values of each expression change as x increases. The big thing to look for or to pay attention to are growth factors. And we see on the expression 10x squared that the growth factor, it starts by increasing by a multiple of 4, but then that multiple of 4 doesn't apply anymore. Here this would be 2.25. Then we have times 1 point something. And so as we notice, the growth factor does not stay the same. It actually starts getting smaller. Whereas our exponential function over here, we'll notice that it's doubling every single time. That growth factor stays the same. For number 2, when you're predicting, there's really no wrong answer there. So go ahead and make those predictions. For number 3, finding those values, here they are at the bottom, and you're just plugging those values in for x into your expressions. And then number 4, make an observation about how the values of the two expressions change as x becomes greater and greater. We've already talked about that. They both keep increasing, but in our quadratic function here, that growth factor does not stay the same. In fact, the growth factor keeps getting smaller. In the exponential function here, the growth factor does stay the same. And something that's kind of interesting, you've probably noticed in the news a lot of talk about exponential growth with the coronavirus. And so that exponential function, you'll see how it's happening there in real life. I do encourage you to graph both of those on Desmos so you can see exactly when the exponential function becomes greater than the quadratic function. In number 2, the quadratic function is g of x, and the exponential function is f of x. And number 2, we're talking about that the exponential function f of x will eventually be greater for larger and larger values of x. And again, that's because your growth factor here is staying the same. In the quadratic function, there is no constant growth factor. In number 4, looking at why the exponential function will overtake the quadratic function. And it's because, again, in the exponential function, we have a constant growth factor here of 4. Every single time it is quadrupling as it gets bigger. In the quadratic function, it keeps getting bigger, but that growth factor changes. The growth factor actually gets smaller. So in the first one, we're multiplying by 4, but then multiplying by 2.25, then by 1.78, and then by 1.56. It's just going to keep getting smaller as you go. And so because the exponential function is quadrupling each time, it will eventually be larger than the quadratic. In number 5, here we go. For number 1, the area of this shape in step 10 is going to be 119 centimeters squared. And because of the pattern that's growing here, I noticed that the side length is going to be 1 greater than my step number. So the side length is 11. And to find the area, I take 11 times 11. That's 121. Subtract off those 2 squares in the corners, so I'd have 119. Number 2, now we're just going to generalize that to step n. So again, the side length is 1 greater than my step number. And I'm going to multiply that by itself to get our area of the square. And then I'm going to subtract 2 because I'm subtracting 1 from each of those top corners. And so this is the area of shape n. And number 3, explain how you see the pattern growing. Well, we're just putting that into words. The side length is 1 greater than the step number, and we're subtracting off the top 2 corners. In number 5, you're just interpreting what's going on in the graph here. The true statements are going to be A, C, and E. The rocket is launched. That's its starting point right here from a height less than 20 feet. This line right here is 20, so it's going to be less than that. C, its maximum height is after 3 seconds. 3 seconds is right here. That would be its maximum height, and the maximum height would be about 160 feet. Number 5, these would be the values that would fit into that table once you take your values for t and plug them into the equation up there. This is what it looks like when it's graphed. And is the baseball traveling at a constant speed? No. If it was, it would be a straight line. It would be a linear function. That's your constant rate of change. But we see that it does not have a constant rate of change. We actually have, it would be a curved line if we connected it, and so no, it is not traveling at a constant speed. Number 3, the correct answer would be table B. this one is a little bit different than what you see in your book. In your book, we talked about this equation for the distance that something has fallen if it's dropped. 16 is your acceleration due to gravity, so that is constant on Earth. But we'll notice here in this table that if you plug in these values for t, that it does not give you these values for the distance fallen. But I do notice that if I did plug in numbers like this, 0, 1, 2, and 3, then I get these same numbers. And so a couple things could have happened here. Maybe we just didn't start the watch until it was at 1 second. We didn't record time or record any heights until we were already at 1 second. And we could just rewrite this equation up here as 16 times t minus 1 squared. And you'll notice now if I plug in these values for t, I will get these values for the distance fallen. A does not work because A is a constant rate of change. It's adding 48 feet every time. And we know that if something is falling, it's going to get faster and faster and faster. And it's not going to have that constant rate of change. C and D don't work because it's looking like it falls a shorter distance with more time. And that doesn't make sense logically. If you drop something for more time, it's going to fall farther. Okay, here's number 5. The correct answers here are E and F. And here's why. If I take, let's say, step 3 as my example, I notice that one side is the same as my step number. So I'm going to call that side n because it's the same as a step number. The other side is one more than the step number. And if I want to know how many squares, I'm going to take length times width. And so I'd have n times n plus 1. The other way to look at this is with F. And where I see n squared would be right here. I have a square where my side lengths are the same as my step number, or n. And then I have to add on this last row over here, and I notice that that is also the same as my step number, n. And so the big square here would have an area of n squared. And so then I would add on n to that n squared. So it's two different ways of looking at the same pattern, two different expressions to show that. And number 6, in this one, B is going to be the correct answer, and here's why. That 16t squared that we saw in the lesson is going to give you the distance that something has fallen. But if we're starting at 100 feet and it's falling, right, and we want our function to show us the height off of the ground, well, we're going to subtract off how far it's fallen. And so as an example, if we did this after 1 second, I would plug that in for t, and 100 minus this would all equal 16 is 84, meaning that after 1 second, it's now 84 feet off the ground. And so that would mean if we started at 100, right here, now we're going to be down to 84. After 1 second, it's just going to keep falling, and that makes intuitive sense. And so B is the correct answer there. In number 8, no, we are not going to agree with Diego. One way to give a good explanation as to why you don't agree with something is to give a counterexample. And so here's my counterexample. If x equals 6, then the quadratic function has a value of 46, and the exponential function has a value of 64. And so the exponential here is greater than the quadratic. So no, the quadratic is not always going to be greater than the exponential.